Alright, everyone. So this will be the last section that we'll cover for this chapter. I'm kind of grouping essentially like the last. If you notice, there's like three more sections in the flex book, and it kind of one of the most important parts of it. So the assignment will kind of be a hodgepodge of different problems. So make sure you pay attention to which problems you need to do specifically from each section. Okay, but we're mostly going to talk about solubility. And what solubility is it describes the mass of solute that dissolves in a saturated solution composed of a specific mass of a solvent at a specific temperature. So what that means in layman terms is essentially that solubility tells you how much of a solute you can dissolve in a certain amount of solution at a temperature. Okay, because each specific thing has a specific amount it can dissolve in before it becomes like supersaturated. Okay, and that's where those supersaturated solutions come from. That if you go over this solubility, you become a supersaturated solution. Nothing else dissolves in it. And as you'll see, solubility of most solids, not all solids, but most solids actually will increase as temperature increases because as temperature increases, you're actually evaporating water, or most of the time, which is the solvent, which means that your solubility is going to decrease because you're going to have less amount of solute in order to dissolve in there. So looking at that and how it actually looks in a curve, okay, something like this. Okay, each of these lines represent a different type of solid. Okay. On the x-axis, you have the temperature at each case, and you see here the solubility is measured in grams per 100 milliliters of water. So this tells you the y-axis how much of each of these solids you can dissolve at a certain temperature. So let's say, for example, about at room temperature, which is approximately here. Let's say we're looking at glucose. So if we go up to glucose, we meet here about 100. That means at room temperature, the most amount of glucose that we can dissolve before it becomes supersaturated is 100 grams in 100 milliliters of water. Okay. Now our water level can change, obviously, but we can use that ratio to see how much glucose can dissolve at most. But this ratio is how much you can dissolve before it becomes supersaturated. Anything higher than this ratio, that means if you add anything more on top, then it will become a supersaturated solution. So these will tell you what's the most you can dissolve before you become supersaturated, before you just have solid collecting at the bottom. Now, there are some factors that affect solubility. We talked about how things can dissolve and stuff. One thing is structure, and we talked about a little before how like dissolves like, and that related to polar and non-polar things, right? If they both were polar, right, they would dissolve within each other. If they both were non-polar, they would dissolve. We saw that with those hydrocarbon chains, right? If I mix H2O and NH3, they will dissolve because they're both polar. But if I mix H2O with like a hydrocarbon chain, C3, CH2, CH3, they will not dissolve because this is, remember, non-polar. So it's going back to how the structure, how it looks, affects polarity and then how that will dissolve within each other. The other thing is temperature, and that's what we just talked about, how most solids solubility will go up with temperature, right? And another way to look at it is recrystallization. Okay, this is a really important thing. This is what we use a lot, especially if you ever take organic chemistry. So if you ever take organic in college, you use recrystallization a lot in those labs. Okay, because that's how you get the purest way to get a solid. Okay, that is the easiest, simplest, purest way to get a solid when you're in a procedure. And how that works, recrystallization, is your goal is to create a saturated solution at the highest temperature. So usually when you have a compound, you know the solubility of it, and your goal is to create a saturated solution at the highest possible temperature you can. Once you have that solution at a high temperature, you are going to rapidly cool it. So most of the time you'll put it like in an ice bath. Okay. What that ice bath allows it to do is that by dropping the temperature drastically, you're going to create a supersaturated solution. And because of that supersaturated solution, from the saturated, you're going to have solid from that solution start to precipitate out. So you're going to have solid now being created from that solution at its purest form. Okay, because there's nothing else it can combine with. It's going to form that pure solid, and you're just going to get crystals forming in that solution as it cools and as you induce it. So that's what happens in recrystallization. It's a really straightforward thing. It's really easy actually. Because like let's say you start with the beaker. Here's your fire. Here's your solution. Here's some things in there, right? And then you have a ice water bath. I'll put it as blue, right? And then you stick that same beaker in it right away, right? Right after. So ice water in here. As soon as you cool it, and how you also do it is you actually take like a spatula, those metal spatulas we have in the lab, and like you scratch the surface actually, you'll start to produce pure solid at the bottom of the beaker. And then once you have enough pure solid, then you filter it out. You have solid, you dry it, boom, you have your product. All right, moving on. Now we're going to talk about gas solubility real quick. So it also affects, so we talked about solids. Now we're going to talk about how gas solubility can actually look at it too. And how gas solubility works is like the most common thing you've seen of it is carbonated water, right? Whether it's pops or carbonated drinks, right? That's a gas soluble, that's gas being dissolved in a liquid. Another example is like oxygen dissolved in lake or ocean water. This oxygen being dissolved is how fish breathe, right? Yeah, they take in water, but they use the oxygen that's dissolved in water to breathe actually. Blood is another example where you carry oxygen through your blood. That's how you actually do that. And same thing as before, where we said temperature can affect solid solubility, it also affects gas, and pressure can affect gas solubility. Okay, so both temperature and pressure can actually affect it. But it's the same sort of concept, just dealing with gases most of the time in liquids. So how the temperature actually affects gas solubility is that the solubility of a gas decreases as you increase temperature. So they're inversely related. So the higher temperature I get, the lower my gas solubility actually becomes. And you actually see this a lot in soda, right? This is a really common example in soda, where if you actually take a warm soda can, you guys can actually try this. Okay, if you have pop at your house or anything carbonated works in a can. You take one out, leave it outside, right? Go put one in the fridge, okay? And then when the cold one becomes cold enough, like actually cold, not like 5 minutes in there, guys, okay? And you open them both at the same time, there will actually be more bubbles in the warm soda than the cold carbonated one because you have more CO2 coming out of the solution at room temperature because the solubility of it decreased as you increase the temperature. So more of it will actually come out. Like I said, you can actually try that and it will be true. As long as you have the same sort of can. Don't use like something different because everything else uses different solubilities. And then pressure. Okay, pressure can also affect it, but the higher the pressure, the more soluble. So this is the exact opposite of temperature and gas solubility, where they're directly related. You have an increase in pressure, then you will have a there we go. You will have more solubility of a gas in a liquid. And again, soda pop is a prime example of this. Okay. The reason why that you hear the pop when you open a can, okay, the actual pop, is because of the high pressure built up in there. Okay. And when you open it, that pressure is released and the solubility decreases dramatically, resulting in the bubbling, which also the temperature can affect how much it bubbles. So they're both related to the same phenomenon, a carbonated drink. Now we can also look at how we can quantify the solubility of gases with an actual equation. This is called Henry's law. Okay? Yes, it was a guy actually named Henry that actually came up with it. And again, like I've talked about, I wish I was one of those guys. But we can quantify solubility. If we look at S as solubility of a gas, okay, that's going to be equal to KH. And what KH is just a constant. Okay, that is basically the gas and temperature at specific constant. So KH equals the gas, and I'll abbreviate temperature temp, specific constant. And this is measured in usually in moles, per liters times atmospheres. Okay. So you'll have solubility equal to this constant times just your pressure, okay? And this pressure is going to be the partial pressure of the specific gas. So we talked about partial pressures a while ago, which was the pressure of one gas in a room of gases. Exerted by the gas in question. Okay, and again, this is always measured in ATM. So we have solubility equals to the constant, the specific constant measured in moles over liters atmospheres times the partial pressure of a specific gas we're looking at. So if you look at it actually, if we have moles over liters times atmospheres times atmospheres, atmospheres will cancel out, and then the units for solubility will actually be moles over liters or molarity. So there we go. So let's look at a problem we can use real quick, and then we should be good. Just one problem today. So what is the pressure of carbon dioxide required to keep the carbon dioxide concentration in a bottle of soda pop at 0.12 molar at 25 degrees Celsius? Okay. So how that works is we are going to use our Henry's law equation. Okay. And when we use Henry's law equation, okay, we're going to look and see what they give us. So we're going to look at solubility, which we talked about before, which is measured in molar. So that's that guy. So we have 0.12 molar equal to, now we don't have this constant, okay? But I would give you this constant actually, or you have to find it, but the constant actually for CO2 is 3.4 times 10 to the negative second molar atmosphere. Okay, so we'll take that, plug it in here. And then we're just going to solve for P. That's all. So we're going to divide this over, solve for pressure, and we get 3.5 ATM. So this is actually how they figure out how much pressure needs to be in the can of pop, or a club soda in this case, to production, right? This is actually a really simple equation that people actually used in production lines to figure out how much pressure needs to be in the can, okay? Because they always need a specific amount of molarity of the gas in the solution, okay? In this case, the carbon dioxide in the solution at a specific temperature, right? So they're going to actually use this equation, use the constant for carbon dioxide to figure out what the pressure needs to be in the can, and they use that same pressure in every can. But that's solubility nutshell for you guys. So make sure you look at what's posted on Classroom for the specific problems I'll have you do, because it's kind of a hodgepodge of different problems.